Hi everyone, and welcome to Simple Science. Today we are going to talk about the conjugate base and in terms of their stability and their strength. So, first of all, a general rule that we have to know is the more stable the anion that the base can be formed, then it will lead to a more stronger base. So, now the first concept is based on the electronegativity, and we compare the conjugate base, the strength of the conjugate base based on their electronegativity. So if we look through the periodic table, in terms of their period, then we will get something like the carbon and then the nitrogen, the oxygen, and the fluorine. And as we move on to the right side, we can say that the electronegativity, or the En, is more stronger, and therefore the atom has more ability to attract the electrons to form a more stable anion. So the more stable the anion, then it will be the more stronger the base. So if you compare a base that have the fluorine anion and the oxygen, then we can say that the fluorine in terms of stability is much more stable than the oxygen because it is more electronegativity. It can hold the electron better than the oxygen. So in terms of anion size, we have to look through the periodic table in column. So if you look through the column, for example, the anion, the fluorine, the chlorine, the bromine, and iodine, just an example. So you know that the trend goes down. As the trend goes down, the anion size is actually increasing, and increasing in anion size, it actually can delocalize the electrons better. So delocalize means spread out. The electron can spread out better, and therefore the electron repulsion force is much more lower, and therefore it can form the more stable anion, and hence the more stronger the base. So if we compare the anion I negative and F fluorine, then we can say that the stability of the anion of the iodide ion is more stable than the fluoride ion, and this is actually different in their concept in the electronegativity. So if we look through the electronegativity, then we are looking at the period, but if we want to figure out the relationship of the anion size and their stability of the base, then we have to look through the column. So now let's talk about the inductive effect. So let's say we have a compound, we have an alcohol. So, and here we have a chlorine. So it basically will gain the electron in the bond, right? Let us redraw it with the purple color. So it will gain the electrons by in the carbon. When the electron can be spread out, can be delocalized, then this chlorine atom can gain the electron so that the electron can delocalize throughout the compound. So if we compare two compounds, so the second compound is something looks like this, then we can say that now we compare the position of the chlorine atom. So we can see, obviously, we can see that the chlorine atom in this second compound is much more closer than this oxygen, right? It's much more closer than this oxygen. So we can say that the inductive effect is more stronger. And actually, the inductive effect means that the spread out of the electrons. So the more spread out the electrons, the more stable the compound or the base is. So this one we can say that this is more stable because the chlorine atom, or the more electronegativity atom, is much more closer to the oxygen. Now let's talk about solvation. So let's say we have a compound, also an alcohol. Let's say we have a compound and alcohol, and a compound also alcohol, but now it has more carbon attached to it. So something looks like this. So if you compare them, this carbon has a carbon group attached to it, but however, this carbon, it has 3 carbon attached to it, and basically when they dissolve in water, we can say that this oxygen will react with the water molecule, specifically the hydrogen, okay, to form the hydrogen bond, right? So something like this. So they will form the hydrogen bond, and same as this case, but however the only difference is that this alkyl group is actually creating the steric hindrance, that will hinder the hydrogen bond can be formed. It will actually decrease the potential for the hydrogen from the water molecules to attach to the oxygen atom. And this is because of the electron-electron repulsion by the 3, or we can say the bulky alkyl group. So in terms of stability, we can say that this is much more stable. So the less branches means that the much more stable in terms of their solvation. So now let's talk about the hybridization. So in terms of hybridization, we know that carbon has sp, sp2 and sp3 hybridization. So there are some difference between the sp, sp2 and sp3 hybridization. Okay, so sp3, we know that it is actually the tetrahedral shape, which is something looks like this, right? So for example, and the tetrahedral, the sp2 is their molecular geometry shape is the trigonal pyramidal, and for the sp is the linear. Alright, so but this is not important actually. The more important things is that the sp3 contains the 25% of s character and 75% of p character. As you can see here, we have 3 p orbitals, so it consists of 75% of p characters. And for the sp2, it contains about 33% of s character and approximately 66% of p characters. And for sp, it possessed 50% of s characters and 50% of p characters. So we want to compare the s characters in each of the different shape. So if you compare them, we can see that along this trend, the s character is increasing when the p orbital is decreasing. So we can say that the sp is much more stable than sp2 and is much more stable than the sp3, and this is because as the s characters increase, it actually means, okay, we can say that it actually means that the electron density is more closer, and therefore it is actually much more better to be controlled by the charged particles, which is the proton. Or we can say that the more stable, then the stronger the base will be. And that's all for our video. Thank you. If you like this video, please subscribe and follow our video for the future.